Okay, Born-Haber cycles are pretty much the culmination of everything having to do with Hess's law and energy cycles. They are really complicated energy cycles for the formation of ionic compounds. And it's really best explained by looking at an example. So in an effort to not use sodium chloride, again, as the ionic compound, we will use potassium chloride to be a little bit different. So what is the chemical equation for the standard enthalpy of formation of potassium chloride? So you should know at this point what a standard enthalpy of formation is. You're forming a compound from its elements under standard state conditions. So potassium chloride comes from potassium, which is a solid at room temperature, and it comes from chlorine. Chlorine is Cl2 gas at room temperature. I need to keep it as Cl2 since that's its natural form at standard state conditions. And so I add the half because when we do formation enthalpies, we should always get 1 mole of the product. And ionic compounds are solid at standard state conditions. So this is the enthalpy change of formation. This can be carried out experimentally, and the enthalpy change can be measured. But that's the chemical equation that represents it. Now, in order to make an energy cycle, we're trying to think about what are all the smaller little changes that we can undergo that would add up to this overall reaction. So if we think about some of the enthalpies that we've learned before, we've talked about the lattice enthalpy. So lattice enthalpies have to do with ionic compounds, and that's the enthalpy change for the KCl solid to turn into K plus and Cl minus, both in the gas phase. And we know that's a big endothermic change to take a solid ionic compound and vaporize it apart into gaseous ions. Now, these gaseous ions, if you hearken way, way, way back to the periodic trends topic and the atomic structure topic way back before, we do know changes that involve forming these ions. One of them looks like this. And if you can remember what that is, I'll be impressed, but that is called the ionization energy. The energy to take a gaseous atom and remove an electron from it is called the ionization energy. So if we keep a tally going on the side, we got lattice enthalpy. Right here we have something that we've done before called the ionization energy. There's a similar value for negative ions, for anions. If we take a Cl atom and we turn it into a Cl minus atom in the gas phase, we do that by making it gain an electron. That is called not electronegativity, but the electron affinity. Okay, so we're doing okay. Now we know how we've got steps where we're, if we flip this top one, so I think about it that way. Remember, I'm trying to create the energy cycle here. So if I want equations that will eventually add up to this final equation for the formation, I could flip this and I'll get KCl solid in my product side. So it looks like maybe I'm going to have flipping the lattice enthalpy, getting the opposite of lattice enthalpy involved in my energy cycle. Over here, I've got the formation of the K plus ion, and I've got the formation of the Cl minus ion, which is good. So now all I have to do is figure out how the heck do I get K and Cl to be gaseous atoms. Well, chlorine's pretty close. Chlorine starts off as a gaseous molecule, and we actually know the enthalpy change to split Cl2. If I start with a half Cl2 and I split it apart into just a Cl, well, that's a bond enthalpy. I've just broken a covalent bond. Because I'm only doing half a mole of the Cl2, technically this is half the bond enthalpy of the Cl2 bond, but it's definitely an enthalpy change that we've seen before. And the last one, which maybe we definitely haven't done before, is what is it called to take potassium solid and turn it into potassium in the gas phase? This gets a new name. It could be called the enthalpy of atomization, which is a cool name, but you could probably also call it the enthalpy of sublimation, and you'd be okay as well, because you're taking a solid and you're trying to make it go directly to the gas phase. So if you take these enthalpy changes and we think about our simultaneous equations, right, and you go through them, let's make this red now. Okay, so I've flipped this one, and I've made it a negative lattice enthalpy, and that's what gave me this equation here. Here's the ionization energy, and that has canceled the K pluses. Here's the electron affinity, which has canceled out the gaseous Cl minuses. The ionization energy and electron affinity cancel out the electrons. I've now canceled out the Cl gas, gaseous atoms, now that I'm using the bond enthalpy, and I'm canceling out the potassium gas with the atomization enthalpy. And overall, what's left? K solid, half a Cl2, and KCl on the right. Now, I would never expect you to come up with all those things on your own. That was just my way of listing all the enthalpy changes that we're going to be looking at in a Born-Haber cycle and showing you that they do, in fact, add together if you have opposite lattice enthalpy, ionization energy, electron affinity, bond enthalpy, and atomization. You can add them together in such a way that they add up to the same exact chemical equation as the enthalpy of formation of ionic compounds. And that's what a Born-Haber cycle is. Oftentimes it gets represented on an enthalpy level diagram. It doesn't always get represented on one of these, but it's fairly common for it to be represented on an energy level diagram. So we've got potassium solid, we've got chlorine gas. I think it's helpful to think about these things in stages. Otherwise, you've got a lot of different enthalpy changes to keep straight. And so I think kind of categorizing the changes is helpful. So for me, I would say, first, let's think about turning the potassium into a potassium ion, and then, or turning it into a gaseous potassium ion, positive ion. That's going to involve two changes. First, turning it into a potassium atom, which we said was the enthalpy of atomization. And so down here, this would be K is now in the gas phase. And then we could turn it into the potassium ion here. So it's K plus, and that was the ionization energy. Okay. Now, when we go along here, we should keep writing these other guys, even though they're not getting changed yet. Essentially, all I'm doing is I'm taking those exact same enthalpy changes we just talked about with simultaneous equations, and I'm now trying to represent them a little bit more graphically and visually with an enthalpy level diagram. So this first change was the atomization enthalpy. Second change was the ionization energy. Obviously, you'd like to label this as delta H, and then with a little AT subscript, but like the little F subscript here for formation. I'm just writing them like this for the sake of ease with this notebook program. Okay, so I think about in one step, or these two steps, let's form from potassium, let's form the potassium ion in the gas phase. And then I'm going to take another two steps to form the Cl minus ion in the gas phase. First, I'm going to break that bond apart and form the Cl atom, gaseous atom. And so to do that, take these guys again. Let's get that. Okay, but now it's no longer half a Cl2. That enthalpy change is called the bond enthalpy, where I've now split the Cl bond. But technically it's half the bond enthalpy because I only used half a Cl2 molecule. The next enthalpy change is the first one, and besides the formation, the only one that's exothermic. Electron affinities, because it involves an atom absorbing an electron, it involves attractions coming together. That's an exothermic change. And so this next change, which brings us down slightly to here, is the one that's called the electron affinity. And here we are now. And so now I'm ending up with Cl minus. And then the very last change, and the one that really overall is the most important for why enthalpies of formation of ionic compounds are exothermic, is this one. Now, drawing it down like that is actually a little bit incorrect because of how lattice enthalpies are defined. Lattice enthalpies are defined as the enthalpy change to take the potassium chloride solid and to have it form these gaseous ions. And so technically that arrow should be drawn up. Okay, so this one is the lattice enthalpy. Okay, so this is a Born-Haber cycle, completely drawn out. You've got the enthalpy of formation here. Enthalpies of formation of ionic compounds are always going to be exothermic. The ionic compound is generally much more stable than the metal and nonmetal that formed it, so there's a big energy release. And the main reason why it's so endothermic is because of that lattice enthalpy. When the gaseous ions come together and form potassium chloride, it is extremely exothermic to do that. So the opposite of the lattice enthalpy would really be the reasoning for why it's so exothermic. The electron affinity is slightly exothermic, but not significant enough to really mean the formation is overall exothermic. These other ones are all endothermic. Turning solid to gas is endothermic. Ripping off an electron is endothermic. Breaking covalent bonds is endothermic. But this is how the Born-Haber cycle fits together. Okay? So which of these enthalpy changes are listed in the data booklet? Well, I'll go over that on the one of the next slides. But the lattice enthalpy we've seen is listed in the data booklet. The ionization energy and electron affinity are listed in the same table in the data booklet, and the bond enthalpies are listed in the data booklet. The formation values are not for ionic compounds, nor are atomization values. So which enthalpies are you commonly asked to solve for on these questions? Well, you're asked to solve for enthalpies of formation of the ionic compounds, and you're sometimes asked to solve for enthalpy of atomization for the metal. Those are the most common questions that they ask regarding Born-Haber cycles. Besides constructing them in their entirety like this, they usually ask you to solve for one of these because they're the ones that aren't listed in the data booklet. So I said, no, Born-Haber cycles are often but not always represented on enthalpy level diagrams. If it is, like in this example, it was important that I drew the arrows pointing in the right direction for endo-exothermic. So it's important to know which of the enthalpy changes are technically endothermic, atomization, ionization energy, bond enthalpy, and lattice enthalpy, and which are exothermic. And so that's formation and electron affinity. Yeah, there's a lot going on here, but if you do a few practice, you realize that they're all kind of the same. You just have to keep all the players organized. So these are the enthalpy changes that are involved. Again, if we want to summarize, technically we've got endo, and actually these first four are all endothermic. So I will make them blue. Nice, I'm thinking about them being cold. And these ones are exothermic, so we'll make them red. Okay. Just a way to summarize. If you look back at the Born-Haber cycle, this equation sort of sets it all equal to the standard enthalpy of formation, that you can either do the formation in one step, or you can form the, I've got it broken down into steps here. You can form the positive ion, gaseous positive ions, by doing atomization and ionization energy. You can form the negative ion, half a bond enthalpy, electron affinity to make it a negative ion, and then you subtract out the lattice enthalpy because you're thinking about now the gaseous ions forming the ionic compound. So it's the opposite of how the lattice enthalpy is defined. So that's one way to sort of separate out this this Born-Haber cycle. If it's, obviously you want to set this, be able to set it up graphically, but it's also, you're going to be asked to solve for things, and it can be a bit tricky to figure it out if you're not a visual person. So here's one equation that you can try to remember in your head. It is complicated, I recognize that. So again, break it down into the positive ion formation, the negative ion formation, and then the lattice, I don't know what I'm doing there, the lattice formation over here. So I break it down for myself. Another way, if you are more of a visual person, you can split it and look at, if you look at all the way from the beginning, trying to think about setting the enthalpy changes equal to one another. So from the very bottom to the very top, there's two different ways you could add it up. You can either look at the lattice enthalpy and the electron affinity as one way to get from this very bottom line to this very top level, right? These two enthalpy changes combined. Or you can look at bond enthalpy, ionization energy, atomization, and formation. So again, all those add up. So these two changes, lattice enthalpy and electron affinity, should add up in terms of their magnitude to these four enthalpy changes. Okay? So I'm going to erase these for the sake of note-taking. But that's the idea. That's what the next equation is going to show. I'm trying to come up with ways to make this make sense for your math, for solving for different values. And so for me, this is another way I think it's helpful to think about it. I've made the two exothermic ones positive. I'm just talking about their magnitude. But essentially, if you want to add them up, another way to do it is that the enthalpy of formation, atomization, ionization, and half the bond enthalpy, if you're looking at them all, just their magnitude, their absolute values, those should add up to the electron affinity plus the lattice enthalpy. Again, just their absolute values. Neither one of these are very intuitive or straightforward. I wish they were simpler equations. But if you like to lock onto an equation rather than a big complicated graph, a visual, then these are two equations that work. The questions often give you, formation and ask you to solve for atomization, or they give you atomization and ask you to solve for formation. So you need to just plug the other ones in and you can solve. To show you the data booklet, table 8 has ionization energy and electron affinity at the top left and right. Bond enthalpies are in table 11, and lattice enthalpies are in table 18. And the last thing to point out is there's one sort of twist that can happen, which is that ions with +2 and -2 charges, they have additional steps. Instead of just one ionization energy, you now have to carry out two ionization energies. The first and the second. The energy to remove the first electron and the energy to remove the second. The second ionization energy would have to be given to you on the test. It's not listed in the data booklet. You'd also have two electron affinities, right? So a first and a second electron affinity. For most atoms, the second would have to be given to you, except for oxygen. If we look back at table 8, here, and look up here at oxygen, there's actually two values listed for oxygen, and there's for sulfur. So pretty much, if you're going to get a question with a second electron affinity, it's going to be one of these two atoms, or they're going to have to give you the value. So oxygen's second electron affinity is positive 753. So that brings up an important point, which is that it might be given to you for oxygen, sulfur, but let me get past this point. The second electron affinity is endothermic. So while the first electron that an atom gains causes stabilization and a release of energy, the second electron that an atom gains actually requires energy to make that change happen. The reason being, when you have O minus and you try to add an electron to it, well, if they both have a negative charge, then they repel each other. And so to force them together to become O2 minus actually is a endothermic change. So the first electron affinity is always exothermic. You've got Z effective coming together like this, Z effective coming together with that electron, and that change is going to be exothermic. Then the second electron is endothermic. And so this would be the trickiest type of thing they could throw at you, is if you are forming something like magnesium oxide, you're going to have to remember to add up 2 ionization energies. So 2 changes in the positive direction for both those ionization energies. The first electron affinity brings you down, but then the second electron affinity brings you back up. Other than that, you've got your lattice. Well, let me flip that again. You got your lattice enthalpy, which is endo. You've got your ionization energy. Oh, we did those. Sorry, we got your atomization, and so here we've got the formation, right? So again, I did this without labeling things, but we got atomization. You got first and second ionization. Here you'd have the first electron affinity, whereas this second up arrow is the second electron affinity. Over here we've got the lattice enthalpy, and here we've got formation. And I realize now that I left one out, which is the bond enthalpy. So that would probably want to have here bond enthalpy. I'm going to pull these down to have it make a little more sense how it's shown. And there it would be, the very complicated Born-Haber cycle that would involve ions that are +2 and +1. Atomization, first and second ionization energy makes the 2+ ion here. And then half bond enthalpy, first electron affinity, second electron affinity to get you up there. And then the reverse of the lattice enthalpy brings you down all the way to the ionic compound at the end. Okay, so that's sort of extreme. We'll probably want to review that one in class. That's the basic premise, and there's a practice problem which you don't need to do now. We will try setting this up together in class. So Born-Haber cycles, rather complicated energy cycles for ionic compounds involving their formation, or all of the tiny little steps that would also form that ionic compound. And usually you're solving for either the enthalpy of formation or the enthalpy of atomization.